To calculate the total mass of the solar system, we are going to build a running mission control ledger, adding the planets up one by one. This diagram illustrates a core rule of scientific notation. The exponent is a unit of measurement. Just as you cannot combine 3 feet and 4 inches into 7 of anything, you cannot directly add quantities that have different sized exponent units. We start our ledger with Venus and Earth. Venus is about 5 times 10 to the 24th kilograms, and Earth is 6 times 10 to the 24th kilograms. Notice the exponents are exactly the same. Because units match, simply add the front digits. 5 plus 6 gives a temporary total of 11 times 10 to the 24th. But this total violates a strict rule. In proper scientific notation, the front digit must be between 1 and 10. 11 is too large. This image demonstrates the fix. We shift the decimal 1 place to the left to get 1.1. To maintain the number's true value, every step the decimal moves left requires the exponent to tick up by 1, from 24 to 25. Checking the final digit and renormalizing if necessary is a mandatory security checkpoint. It keeps every entry in our universal ledger mathematically valid. Next, we add Mercury to the ledger. As a small rocky planet, its mass is a fraction of our running total. Mercury's mass is 3 times 10 to the 23rd. Our ledger's running total is sitting at 10 to the 25th. The exponents do not match. To make these numbers interact, we follow a strict protocol. We must rewrite the smaller exponent so it matches the larger one. To bring Mercury's exponent up 2 places to 25, we compensate by shifting its decimal point 2 places to the left. 3 becomes 0.03. Now the units are aligned. With matching units, we combine the front digits. 1.1 plus 0.03 locks in our new terrestrial running total, 1.13 times 10 to the 25th kilograms. The exponents dictate the rules of engagement. Treating them as rigid units of measurement prevents massive calculation errors. Let's step away from the main ledger for a moment to see how much more massive Earth is than Mars. Earth is 6 times 10 to the 24th, and Mars is 6 times 10 to the 23rd. Once again, the exponents differ, which means we apply our alignment protocol. We adapt the smaller number. Mars's decimal shifts 1 place left, pushing its exponent up 1 place to 24. It is now 0.6 times 10 to the 24th. Now we subtract the front digits. 6 minus 0.6 gives us a final difference of 5.4 times 10 to the 24th kilograms. Whether you are building up a sum or calculating a difference, aligning the exponents is always the required first step. We bring Jupiter into the equation. This represents a massive leap in scale compared to the inner rocky planets. Our terrestrial running total sits at 10 to the 25th. Jupiter's mass is 1.9 times 10 to the 27th. There is a 2-factor gap in their exponents. We adjust the smaller value. The terrestrial total's decimal shifts 2 places left to match Jupiter's exponent of 27. It becomes 0.0113. We add the front digits. The exact sum is 1.9113 times 10 to the 27th. But at standard precision, the combined mass of the inner planets is so slight that the total rounds right back to Jupiter's original mass. This chart displays exactly how vast that gap is. On a logarithmic scale, the terrestrial subtotal barely registers against Jupiter alone. The final combined total is visually indistinguishable from the gas giant. Now it is time to practice this process on your own. Pause the video and solve these 4 equations about the ledger's help. Check your work against these solutions. Notice how question 2 required you to align the exponents first, while question 3 required a final renormalization step at the end to correct the front digit. The process always follows the same logic.